Okay, welcome back. This is the beginning of the 4th week's online lecture, and here we will study chapter 25, capacitance. Okay, just like always, let's make a brief review of last week's lecture before we move on to this week's lecture. Okay, so in the last lecture, we learned the electric potential and its similarity and differences with respect to electrostatic potential energy. And we also learned how to draw the equipotential surfaces. And we also learned how to calculate the electric potential when the electric field is known. And finally, we learned how to calculate the electric field when the electric potential is known. Okay. And then in this chapter, we will study the capacitance. And then take a look at the photograph here. So there are many small and large devices. Can you recognize what these are? Actually, these devices are called capacitors. And capacitors are devices that we use to store electric charges. Okay, and there's another photograph which shows a smartphone here. Okay, I think many of you already have your own smartphones. And why is the smartphone shown here? What do you think is the reason? In fact, the reason is because of this touch screen of the smartphone. You know, you can control this smartphone by touching its screen by your fingers. And then how does the smartphone understand where your fingers are? Do you have an idea? In fact, how this smartphone recognizes your finger is directly related to the physics of capacitance. So once you have learned this chapter, you will be able to understand how this smartphone can recognize your fingers. Okay, so in this class, we will study the basics of capacitors and also the definition of capacitance. And we will also learn how to calculate capacitance for simple cases, and also how capacitors can store electrostatic energy. And finally, we will also learn how dielectrics or dielectric materials can increase capacitance. Okay, let's begin by explaining what capacitor and capacitance are. Okay, a capacitor is formally defined as a system of two isolated charged conductors, plus Q and minus Q, separated by a certain distance with an insulating gap, which means that charges cannot move across from one place to the other. Okay, so and take a look at the figure on the right side. Here we have one conducting object charged with plus Q and the other object with minus Q. And they are separated, so the charges cannot move. Okay, and then the shape looks very funny, right? So for capacitor, the shape doesn't matter. So actually, depending on the shape, some numbers may be changing, but still is a capacitor. Okay, and then if you remember the electric dipole, how is this capacitor different from electric dipole? Okay, please think about it, and we will discuss it in detail in the classroom. Okay, and then let's see how much is charge stored in this capacitor. Well, if you add the total charge plus Q and minus Q, it may actually become 0. But that's not what we mean by we are storing charges here. So even though there is plus Q, minus Q, and net charge looks 0, it actually we are still storing a certain charge on these two plates, plus Q and minus Q. So when we say we store charges here, we do not mean the total charge of the combined total charge of the two plates, but what we mean by that is the absolute value of the charge on one of the plates. Okay, that's what we mean. And then here you can see that electric field lines are going from one side to the other. And then we learned that when electric field is going through a certain distance, there will be electric potential difference. And then let's call this electric potential difference to be delta V. And then using this, now we can define capacitance like this. Okay, the capacitance is now defined as the amount of charge stored in this capacitor divided by the electric potential difference between these two plates. And basically what it means, what it represents is how much charge can effectively be stored per unit potential difference. So basically capacitance shows you how good the capacitor is for storing charges. Okay. And then let's try to think about SI unit. You know, the capacitance is now charge divided by the potential, and then SI unit of the charge is coulomb, and then SI unit of the potential is volts. So therefore, the better way to define SI unit for capacitance is coulomb per volt, but we will have a new name, which we call 1 farad. And then we'll use this large F, capital F. And then can you actually recognize where this name farad may be coming from? It is in fact a name of an English physicist, Michael Faraday, who worked very hard on electricity. Okay. And then let me also mention, in order to avoid confusion, that we sometimes use symbol C for two different cases. The first is that for the unit coulomb, we use capital and Roman C, but for this physical quantity or variable capacitance, we use this capital and italicized C. So if you see the Roman C, then it is coulomb, but if you see this italicized C, that will be the capacitance. Okay. And then if we draw the electrical circuit using symbols, this is the symbol we use for the capacitance. And then here it basically represents two conducting plates facing each other but separated by a certain gap. And then you can see that the two plates or two sides actually look the same. So even though the figure on the top shows the positive charge on the left side and negative on the right side, these positive and negative can easily change in a capacitor. So therefore, actually, there is no predefined polarity or no predefined position where the positive charge has to go in. So therefore, left and right are exactly the same. Okay. Okay. And then this is the example of how this symbol is used in a real circuit. And then there's another symbol which looks similar but a little bit different, which is a battery here. Probably you have seen this from elementary school. And then we draw the symbol for battery with one longer and thinner line and the other with shorter and thicker line. And this longer and thinner line represents the positive terminal of the battery. Okay. And then, of course, a battery has already we know which side has to be plus. So that is the reason why battery has predefined polarity, which is different from capacitor. Okay. And then in both cases, the charges are moving, so therefore currents are flowing. And then how is battery different from capacitor? Can you tell it? In fact, the role of battery is actually maintaining a constant potential difference. So once you have a battery of 1.5 volt, it will be 1.5 volt until it dies. So that is the role of the battery. But for the capacitor, it is different. If you have any given capacitor, the fixed number is this capacitance. The capacitance shows you how good this capacitor is. Then, since the C is a constant, now Q and delta V may change, which means that now the electric potential is no longer constant for capacitors. Okay, so that is the difference between battery and a capacitor. Okay, and then again, using this virtual experiment provided by PHYS152 Colorado University, let's try to learn basic properties of this capacitor. Okay. Okay, here we have a battery connected to two conducting plates facing each other. So the right side will be working as a capacitor, okay? And then this battery has a knob with which we can control its potential difference. And then, okay, right now it's at 0 volt. So let's slowly increase it to 1.5 volt. Okay, as you can see, the arrows represent the current flowing, and then see what's happening. On these two conducting plates, you can see the positive charges are accumulating on the upper plate, while the negative charges are accumulating on the bottom plate. Okay, so and then let's slowly move it back to 0, and then you can see the charges disappear because the currents are flowing out, and then we can put it up to again minus 1.5 volt. As you can see, now the positive charge has moved to the bottom plate, while the negative charges have accumulated on the top plate. So, which means that now the polarity can be easily reversed in capacitor. Okay, and then let's put it back again to plus 1.5 volt. And then here we mentioned that the role of this battery is maintaining the constant potential difference, so we keep it at 1.5 volt. And then here, let's see what happens if you move these plates. You can move the plates up and down, and then we keep them closer. And then, as you can see, the amount of charge increase, right? We again put it, take them apart, and then decrease back. And then, if you again put them close to each other, as you can see, the amount of charge increase. Well, what is going on? So we will discuss this in the next slide. Okay. And then again, suppose we can actually increase the area of this capacitor. As you can see, the total number of charges on each plate looks like they are increasing, right? So we also have to discuss why this number of charges actually change. Okay. Okay, and then let's see again what happens if we disconnect the battery. Here, this button allows us to disconnect the battery. Okay, and then, charges are still staying there, even though the battery does not keep the electric potential. So why is it? Because now here, the wires have disappeared. The charges cannot go out. There's no way to go out. And then, assuming that we fix the position of these plates, these two charges, positive and negative charges, are held together by the Coulomb force, and then it still keeps the electric potential difference. And then in this case, what will happen if we move it up and down? Well, remember when the battery was connected, when we moved up and down, the amount of charge changed, right? But right now, the amount of charge do not change. Actually, it cannot change because there is no wire or there is no route for the charges to flow, right? So the number of charges actually do not change. Okay. In order to understand what we have just seen in this simulated experiment, we have to learn how to calculate the capacitance of a given capacitor. Okay. And then we have seen the parallel plate capacitor, which is the simplest example. And it's also shown here. Here we have two conducting plates facing each other. This is the parallel plate capacitor. And then let's say the area of each plate is A. And then these two plates are separated by the distance D. Okay. And then suppose the upper plate is charged by plus Q. And then the lower plate is charged by minus Q. And then where should these charges go? Actually, we find that the positive charges of the upper plate will all accumulate at the bottom surface, and then the negative charges of the bottom plate will all accumulate on the top surface. Why? It's simply because of the Coulomb force between positive and negative charges. So these positive and negative charges will attract each other, so they will be pushed closer to each other. So that's why they are accumulated on the two faces directly facing each other. Okay, and then here we will try to calculate the capacitance by using the electric potential, which again we need to calculate the electric field. Okay, and then how do we calculate the electric field here? We will use the Gauss law, of course, and then we first have to set up the Gaussian surface, just like here. Okay, and then we will divide this Gaussian surface into three regions. The first S1, and then the S2, which is all the side surfaces, and then S3. Okay. And then let's try the Gauss law. How did we do that? We are integrating electric field with the area vector over the entire Gaussian surface. And then for the S1, so what is the electric field along S1? You know, S1 is inside the conductor. So remember, inside any conductor, electric field will be just 0. So the first part becomes 0. And then for the S2, now the S2 vector is actually going sideways, right? But the electric field is going down, so therefore it's perpendicular. So second part again becomes 0. Okay. And then how about S3? In S3, now electric field we have to calculate. But then you know, if we assume that these plates are large enough, then the electric field will be effectively same whether or not you move sideways. Electric field will be the same. And then again, if you assume that if you try this Gaussian surface with a different height, then again the calculation of the Gauss law effectively becomes all the same. So therefore, it already suggests that electric field is uniform inside this capacitor. So therefore, the third part is simply electric field multiplied by the total area, which is A. And then how much charge is enclosed inside this Gaussian surface is, of course, the total charge of the upper plate, because we are enclosing the whole of the upper plate, as you can see in the figure. So therefore, it will be the Q, and then finally we get this equation. Okay, and then let's try to calculate the potential difference between these two plates. Remember how we calculate the potential difference, and then here the delta V is the potential difference between positive plate and negative plate. So therefore you are integrating the electric field from negative plate to the positive plate. Okay, and then we just said that E is uniform, so therefore E actually comes out of the integral. So therefore, if you integrate ds from negative plate to the positive plate, then there is simply the distance between these two plates, okay, which is d. And then let's finally put these two equations into the definition of the capacitor we know. So we just said the Q is epsilon naught multiplied by EA, and delta V is ED. So therefore, electric field disappears from this equation, and finally we get the capacitance of the parallel plate capacitor, okay, which is epsilon naught A divided by D. So remember, this is the definition of the capacitance. So therefore, it's true for any capacitor, but this is true only for parallel plate capacitor, okay. And then let me throw in two questions. First question is that if you want to make a capacitor with large capacitance, then what do we need to do? Just take a look at the equation here. So in order to get the large capacitance, you either have to make the area very large or distance very small. Okay, that is the method you can make the capacitor with large capacitance. And then the second question is, try to explain what you observed in the similarity experiment using this actual capacitance. Okay, think about it, and we will discuss this in the classroom. Okay.